Okay, let's start. This is the second week of pattern recognition course. Today we're gonna talk about the supervised learning and discriminant learning, in particular linear regression with some terminology. Okay, let's start with the examples. Let's see the examples of predicting housing price, like this. We're gonna use the data set of the price from the city of the Portland, Oregon, and we're going to plot a number of houses. There are different sizes and with the different price like this. So let's say that given this data set, you have a friend who is trying to sell a house, and let's see your friend's house is size of like this, and you want to tell them how much you might be able to sell the house. One thing you can do is just fit the data like this, and you may find the values on this line, and you can say, see, you can sell your house as a price of something like this. So this is the standard kind of the regression problem. So for this regression problem, we need a training set of the house prices, like the size of the house and that correspond the how price of the house, something like this. So we need the historical data for the house prices. So this is the standard examples of regression problem. Okay, so what is the regression problem? Formally, how can we define the regression? So regression is to relate the input variable to the output variable. I mean, input variable, output variable. So, okay, let's see the example. Okay, let's say there is the variable xn lies in the real value with the d-dimensional vector. Do you remember what is variable in the previous lecture? The variable means the scalar or vector number coming from the some kind of probability or some kind of probability density function, something like that. So it is called the variable. So from the input variable, we can find the corresponding output variable. Let's say the yn is also real value. So let's say there are some samples like this. So when we have the input and output pairs from the data, we want to predict the output for a new input. So this is one example of regression. Or we want to understand the effect of the input on the output space. So this is the two kinds of the goal of the regression, like that. So if we have some training set like that, we want to relate the input variable and output variable. Okay, so this is the linear regression. So in the linear regression, we need a data set called the training set, or called the training set. The data consists of the pairs xn and xy. So xn is the d-dimensional input vector, and yn is the output or output variable. So for linear regression, we need the training data or training set. So let's say, okay, so yeah, here's what I mean. So let's say we have a data is consisting of the xn, yn, and n is equal to 1 to the n. So it will be the set of the training data. So this is called the training data set, and we can say this is the number of data set, number of data, or called the data set, a data site, and xn lies in real values d dimension. So in this case, d is called the dimensionality of the input data set. So for the regression problem, we need this, like this data set. Let's see the example. Let's see the example. So we have the data x. Okay, let's use black. Okay, we have a data 1, 2. Say 1, t with the corresponding y1. This is the training data 1, and we have another data samples. Let's say 2,1, yes, 2,2, 2, t, and with the corresponding y2, something like that. So let's say we have n samples, and you can be represent something like this, something like this, something like this. So this is our training data set for regression problem. So as you can see, for training data set, this is a kind of the matrix. Do you remember what is matrix, right? So matrix can be represented by the row by column, right? So in this case, the row will be what? Be n, right? And the columns, number of columns will be the t. Okay, so this is the examples of the training data set for the regression problem. So as you can see here, for the regression problem, we need the ground truth or the output values. So it means that the regression problem is the kind of the supervised learning. So as you can see here, we have a input and corresponding output. Let's find the mapping function between input and output variables. So this is the goal of the regression problem. Okay, so in the machine learning, the input variables are also known as the features, covariant independent variable, explainable variable, exogenous variable, and predictor, something like that. And output variable also known as the target, label, response, output, independent variable, measured variable, something like that. So input variable or output variable can be represent any kind of the terminology like this. Okay, so this is a data set of the regression problem. Okay, so there are two goals for the regression problem. The first one is the prediction. The second one is the interpretation. So okay, so in prediction, we wish to predict the output for the new input vector. For example, what is the weight of the person who is 170 centimeter tall? Okay, so how can I answer that? So from the historical data set, we can learn the mapping function between the height to the weight So it will be some kind of the regression function. So this is a prediction case. In the interpretation, we wish to understand the effect of the input on output. For example, are taller people heavier too? What does that mean? So it means that we want to understand the data set. We want to understand the historical data set, and we want to say the heavier, the taller people's heavier, something like that. So it is also to learn the mapping function between the height to the weight, right? So this is another goal of the regression. Okay, so as you can see here, there's a two goal prediction and interpretation. For example, there are several kinds of questions. What is life expectancy of the person who has been smoking for 10 years? The smoking causes cancer. When the number of the packed smokers smoked per day is doubled, their lifespan get cut in half, something like that. Then what is the prediction and what is the interpretation? So find the answer in yourself, okay? Yourself. Okay. Okay, so to regress the data, we need to find a function that approximate the output well enough if given an image. Okay. We need to find a function that approximate the output given the input well enough. What does it mean the well enough? Okay, let's say xn was the input and yn was the output, right? The goal of the regression problem is to find this mapping function that approximate the output given the input data. Okay, so in the supervised learning problem, we have a training set and we design the learning algorithm. It can be the several kinds of the method, but in this lecture we just focus on the regression problem or regression setting, and we can find the mapping function. In this case, let's say the f, let's all call the hypothesis. And then if we find this mapping function, we can use our input data set to generate the output variable, and then we can check this estimated output is similar to the given output data set or not. So this is a common strategy to solve the linear regression problem. Okay, so let's see the details of before that, I want to say the correlation is not equal to causation. What does that mean? So the regression find the correlation, but they doesn't find the causal relation. What does that mean? So here's an example. So this is the number of flights, and the y-axis means the global average temperature. As you can see here, this graph looks like there is some kind of correlation between the number of flights and the global average temperature, but we cannot say there is some causal relationship between the number of Pareto and the number of global average temperature, but we can say there is some correlation. Okay, it's not a causal result. So interpret your result with the quotient when you use the regression method. Okay. Okay, let's go to the linear regression problem. Okay, so what is the linear regression? So linear regression is the model that assumes the linear relationship between input and output variable. Here's the example. This is the height. This axis is the weight. This each samples mean the training data. And all of these samples make the training set, right? Training set. Okay. So as you can see here, which model can approximate this correlation? I would say if there are some kinds of this straight line, we can approximate this data set well, right? So what I want to do is to find this straight line. To approximate the relationship between the height and width. So what is this straight line means? This is the linear function or linear equation, right? Do you remember what I explained the linear equation in the previous lecture? Linear equation means, let's say the y is equal to coefficient a1 x1 plus a2 x2 plus blah 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 and xn times an times xn, it's like this. This is some kind of linear equation. What was the nonlinear equation? Let's say if there is some kind of x1 times x2 or x1 times square or x1 like this. This is the nonlinear case. But here we want to focus on this linear equation case. Why we learned about the linear regression or linear equation problem? Because there are so many regions, because it is very simple, easy to understand, and most widely used and easily generalized to nonlinear model. We can discuss this later. Anyway, so this is why we learn the linear regression problem, and most importantly, we can learn almost the whole fundamental concepts of the machine learning with the regression alone. So that's why we learn the linear regression method. Okay. So what is the linear regression? We already learned about that, and how can we represent the linear regression function? So let's say there is an input variable and output variable. We want to model the function f, right? Then how can we make the function f? We can introduce some variable w, okay, or parameter w. So with this parameter, we can write the linear equation something like this: w0 plus w1 times xn. Okay, so it means that, let's say that, okay, let's see this example. We have the input variable xn, lies in real values with a d-dimensional vector. But in this case, we just think about d is equal to 1. This is a kind of the very simple linear regression problem with a one variable. And in this case, this linear equation function can be mapped to this straight line here, right? So how can I draw this line? How can I draw this line? We can say that if xn equals 0, this part it should be a w0, right? So it means that this straight line have the point at 0, w0, right? And what is the slope of this line? So this the slope of this line should be some kind of 1 through the w1, right? So we can say that this is some straight line, and it can be represent the f subscript w over x, right? So as you can see our previous example, our question is how to find this straight line, formulate like this. Okay, it means that what does that mean? It means that we should find this parameter w is equal to w0, w1 that describe this mapping function. Okay, so this is the simple linear regression problem setting. Okay, so the learning, the estimation, or fitting having the similar meaning. So it means that given the data set means the input and output pair, we want to find the parameter w that best approximate this training set. Okay, so it is called the learning or the estimating the parameter or the fitting the model. We can say like this for this procedure. To solve this the parameter w0 and w1, we need some kind of the optimization algorithm, so which we will discuss after that. Okay, so this is the overall framework, overall procedure of the linear regression. Then let's go back to the example. Then what is the cost function? What is the cost function for linear regression? Okay, let's see the training data set again. So the input variable was the size in the pit, and the output variable was the price of the house, right? So it means that the x1 was equal to 2,104, x2 was equal to 1,416, x3 was equal to 1,534, something like this, and output y1 was the 416, y2 was equal to 232, something like that, and we have the number of training data set. Let's say there was some number, the number of data set was the 37, something like that. So this was the training data set for our for our linear regression problem. So considering the mapping function, or the model that we discussed previous slide. So it can be represented like the linear regression with the parameter W0 and W1. Okay? So the linear regression problem is that how can we estimate or guess or choose the values of the parameter W given the data set? Okay? So this is just a learning problem. Okay? So from now on, we will talk about how can we define this parameter W and how can we solve this parameter. Okay. Okay. Before that, let's see some example. Let's see some example. Okay, we are just consider the following model such that yn can be approximated by the f subscript w over xn is equal to w0 plus the w1 times xn. Okay, so this is just a regression. Okay, this is just linear regression equation. Okay, how can I draw this? Edge bearing the parameter w0 and w1. Okay. Let's say w0 is equal to 1.5 and w1 is equal to 0. Then this mapping function should be what? This mapping function should be what? In this case, we can write that f w x is equal to 1.5 plus 0 times x, right? So this mapping function should be constant, like this. This should be 0, 1 times 5, okay? Another case. How about w0 is equal to 0, w1 is equal to 0.5. In this case, fw over x should be 0.5 times x. Okay, so in this case, this line is gonna be something like this. Should be 2,1 like this. Or when the parameter w0 is equal to 1 and parameter 1 is equal to 0.5, it should be something like 1 over 0.5x. So it's gonna be here and here. 0,1, 0,2, something like this. So something like that. So as you can see here, as you bearing the parameter set, we can find the best performing straight line for the training data set, as bearing the parameter set, something like this. So how can we solve this the more systemical way? Actually, it's kind of the very brute force, right? Brute force. We cannot consider the every possible combination between the W0 and W1, and we cannot find the W1, W0 and W1 in the similar way. Or if, let's say, there are a large number of the parameter, let's say there is the more than the 1,000 parameter, then we cannot find the parameters like this. So we need the more systemical way to solve this problem. Okay, the ideas are here. Okay, we can say that choose the weight W is equal to W0, W1 so that the mapping function called the f subscript W over the x is close to y for our training examples xn, yn. What does that mean? What does that mean? Okay, let's see the example. Here is some kind of a training sample. Let's say xn, xyn, like this training sample. For example, it can be the x1, y1, and x2, y2, something like this. What I want to do, we want to find this mapping function that can be represented f subscript W over x, and it should be as close as possible with the real output value, something like this, something like this. Then if this error, let's say this is error, or we can represent the en is equal to real yn values with approximated values, something like this, right? So this is value for nth, for the nth training sample, right? So we can say that, okay, so for the linear regression problem, we should find this variable here that minimize this error for every training samples in our training data set. Okay, so this is the formulation of the linear regression problem. Okay, let's use the equation to represent what I said. Here's the example. Let's find the variable W. Okay, so that f wx is close to y, like this. The close means it's kind of the distance, right? Distance or norm. Do you remember the norm? What is norm? If you don't remember, please go back to the previous lecture in the YouTube, so you can find what is meaning of the norm and what is meaning of distance, right? Okay. Anyway, so let's measure the difference between the yn and the fwxn. Okay. For our training example, because the training example, in the training data set, we have the samples, let's say, and from 1 to the n. And what's the number of samples? So we should aggregate this distance among the training sample. Okay, so this is the formal equation for the regression problem that we discussed so far. Okay. Okay, we have equations and we have a function, and we define the distance, and we have the training data set. Then how can I find that? Oh, sorry. Then how can I find this parameter W? So that's the goal of the linear regression problem. How to find? How to find. Okay. That's what I want to do. Before that, I want to make this function in a general formulation. Okay. Let's say, okay, we have an training data set and we define some distance between the real output and estimated output and aggregate these values among the whole training sample. Then let's find the parameter W that satisfies this distance or this norm. Okay, so this is the general formulation of the linear regression problem, but I want to need some more fancy terminology to represent this formulation. So let's say let's define this function. The distance between the real output yn and the estimated output f subscript w over xn, we can say that this is the cost function. So this is very, very important in the theory. Very important. So the cost function. So cost function means. Okay, let's see the formal definition. The cost function means, which is also called the energy loss training objective, something like this, is used to learn the parameter. In our case, it was the W that explain or approximate the data well. So this is the definition of the cost function. So the cost function quantifies how well our model does, or in other words, how costly our mistakes are. Okay, so this is the definition of the cost function. There are two kinds of desirable property of the cost function. Okay, when the target or the output value y is real value, it is often desirable that the cost is symmetric around the zero, since both the positive and negative errors should be penalized equally. What does that mean? Okay, let's draw some plot. Okay, let's go back to the former equation. We was that cost function is the function of the estimated the output of the input xn and the real output value, something like this, right? So in this case, we should measure the distance between these two variables. So let's say this is the error n is equal to fw xn minus yn, right? So then this cost function can be represented by some kinds of the function of the nth error, like this. Okay, so let's say there is some visualization with the error en with the cost function of en. Okay, so the desirable property of the cost function is let's suppose the cost function looks like this, or the cost function looks like this. Okay. In the first example, this cost function is symmetric between positive and negative error, right? And the second cost function is not symmetric across the positive and negative error. So let's say this is the cost function 1, cost function 2. Okay. So we could say that this case is much desirable than this case, because when we measure the distance between the real values and the estimated value, it could be the positive or negative value, right? Let's say if fwxn is larger than the yn, so en should be positive, otherwise en or negative, right? But in terms of distance, these two values have the similar meaning, but they just have the different positive and negative symbol, right? So in that case, in terms of error, these two values should have the similar effect on the our model. But if the cost function is not symmetry across the y-axis, let's say if we have the same distance but they have the different cost function, they have the different effect on our learning model. So it's not desirable, because we want to make our cost function works equally for the positive and negative sample with the same absolute value. So we could say that this cost function is much desirable than this cost function. Okay, so this is the first property. Another property is that our cost function should penalize the large mistake and the very large mistake. Similarly, what does that mean? Before define this, what is a large mistake? Large mistakes means large cost or large error, right? Very large mistakes mean errors of the another sample is very, very large, this large mistake. Then why this property is necessary for the cost function? Because in some case, we don't want to consider this mistake, because it's kind of the outlier, right? In general case, we want to consider the more general samples. We want to find the more general statistic between input and output. But the very large errors or outliers, we don't want to consider this. We just consider the most general case. So it means that we should minimize the effect of this very large mistake. It means that, let's see the example. There are some samples like this, but there are very interesting outlier here. but we want to make our mapping function something like this. But if the cost function penalize the this very large mistake differently, the mapping function should maybe looks like this, right? To minimize this cost. So this is not desirable. Okay. Okay. So we want to find the line looks like this. So this is the two desirable property of the cost function. Okay, let's see the some intuition in the cost function. Before that, let's summarize what we have done so far today. We have a data set, right? We have a data set xn comma yn over n is equal to 1 to the n. This is our training data set. We want to find the mapping function or model that approximate the real output value y with this mapping function. In this mapping function, there are parameters w that define this model, and we can define the cost function that measure the distance between the real output values and the estimated values, and then we can aggregate this cost function across the whole training set, and then we should find this parameter w that minimize this overall loss function. So this is what we want to do. So let's see the very simple case of this whole procedure. We can simplify this original model as considering just one single parameter w1. So let's say our new model will be the w1 times x, and in this case we just consider the w1. So this is just single parameter, and then we want to define the cost function something like this. Let's say we just measure the distance between samples and approximated values as a scared difference. Scared difference means just the scale of the different absolute difference, something like this. And then let's find this w1 is just the constant real values, something like this. So this is our goal. Okay. Here's the example. Okay, so we have the mapping function and we have the loss function, right? The mapping function means for fixed w1, the parameter w1, this is a function of the x, right? So with the fixed parameter w, it can be the function of the x. It means the input of our training data set, right? Then this loss function is the function of the parameter w1, right? Then so first of all, let's consider the very intuitive example. When the w1 is equal to 1, then we can draw the straight line like this, because the w fw over x can be represented like the x, right? Okay, when we see these three kinds of example, 1, 1, 2, 1, 2, 3, 3, this is the training set, okay? So in this case, what is the difference between the real values and estimated value? Okay, what is that? Let's compute that. So W1 is, what was that? Do you remember? What is that? Here, okay? So in our case, n is equal to 3, so it is the 1 over 3 and the summation of the fw xn minus yn over 2 when n is equal to 1 through the 3, right? So this is our loss function. So then what is that? So in this case, 1 over 3 plus the distance between the estimated values and the real values is what? This, let's say the error. So in this case, error is what? 0, okay? So it should be 0, 0, 0. Okay, so it is going to be what? 0. Okay, so it means that if the W1 is equal to 1, the loss function is 1. No, it's 0, right? This is very simple example, right? What about the W1 is equal to 0.5? What about this case? Okay, in this case, the difference between the real values and estimate values are like this, like this, like this. Okay, then what is this point? Because it is the 0.5x, so it should be 1, 0.5, 2, 1, 3, 0, 1.5 like this. So this is 1, 1, 2, 2, 3, 3. Okay, right? Then no, in our case, it's L, right? Then, well, when W1 is equal to 0.5, we can compute the 1 over 3, and how can we measure this distance between this and this? How can we measure? Do you remember? It's like the 1 minus 1 square, 1 minus 5 square, like this, right? So this is the distance between these 2 points, right? But in our case, we have some square term here, so let's say it will be just 1 over 1 minus 0.5 squared like this, and 1 negative 2 squared, and 1 over 3 minus 3 times like this, right? So what is that? So it's be like this, just 1, and like this, right? And 5, 7, 1, 2, 2, 5, right? So it should be, okay, let's move to here. So it should be 1 over 3, times then like these values what? These values what? You can do this by your hand. Let's say it's approximated about 1.1, blah blah blah, something like this. Okay, so we know that when W1 is equals to 1, it was 0, and when W1 is equal to 0.5, it should be somewhere here, right? Right? Okay, so if you remember correctly, the okay, let's see another example first. Okay, what if the W1 is equal to 0? What if W1 is equal to 0? We can also compute the loss function here. Let's say 1 over 3. In this case, this is just the distance between real values and estimate values, so it should be something like this, right? So 1, 4, 9, so times the 14 and right? So 4 points like this, right? So in this case, it should be something like this. Okay? So if you remember correctly, where's that? Here the cost function should be symmetric, right? So it means that this value should be symmetric at the point 1, like this, something like this, right? So if we do this procedure at every point, it can be look like this shape. Okay. You can do similar procedure here and here by yourself, right? Yourself. I highly recommend you to do this yourself. Okay. And then, if we go back to the goal of the linear regression problem, we want to find the parameter W that minimizes this loss function, right? In this case, W is just equal to W1, right? In this case, which values makes this loss function is minimum? In this case, W1 is equal to 1, then this loss function is minimum, right? So we could say that in this case, W1 should be what? This values is just 1, and we could say the solution or the parameter of this learning procedure should be W1 is equal to 1. So this is very intuitive procedure for the what the cost function means and how can you solve this problem? How can you solve the linear regression problem? Okay, let's go to the more complicated example. In this case, we just to consider the very simplified version of this function, but we could do similar these similar things with one more variable, with